Okay, welcome everyone. We will wait for 5 more minutes to see if anybody joins. Then we'll start sharp at 3:05. Okay, so let's begin. This is NOC EE-62 NPTEL tutorial on basic electronics. Rather, it is more of a problem solving session as per the NPTEL norms. The course instructor is Professor Mahesh B. Patil from IIT Bombay. I am Debashish Nandi from IIT Kanpur. I am a PMRF scholar. I am a TA to this course. As you know, this is a 12 weeks duration course, and we are currently at 8th week. Almost 75% of the course material is over. So we go live every Sunday 3 to 5 p.m. So some basic guidelines that I am expecting you to cover the previous week lectures which were posted in the course web page, and also you should have attempted the last week's assignments. So it will help you to go with the pace of this tutorial session, and also help you in grasping the materials, right? So some basic decorums I want you to follow, that please keep your microphones muted all the time. And also if you have any questions, you can use the raise hand option. And if after every problems or topics, I'll give you some time to ask your questions or doubts if you have any. And also as it is a 2 hour session, at the end of the 2 hour, I will try to assign 10 minutes for general doubt clearing, right? Also, it is suggested that you to keep a scientific calculator with you all the time so that you can follow along the material of this tutorial, right? The link of the like in this recorded lectures are already shared by the NPTEL team, which is available on the course web page under the tab of problem solving session, right? So let's begin. So we are at 8th week. So today we will be discussing basically some basic OPAMP circuits, some active filters, and also we'll touch upon Bode plots, right? This is very important concept in you might have read it in control system course, but it is very much essential in any of the circuit analysis, right? So let's begin. So let's move along with problem number one. So what problem number one is asking, that which of the following plots correctly describes the V naught versus VI relationship for the circuit shown in the figure, right? So what is this circuit? This circuit is nothing but a, as you can say, inverting amplifier. Also in the feedback path, we have a Zener diode, right? So what is a Zener diode? This was covered in diode circuit lectures. Zener diode IV characteristics, how does it look like? Zener diode IV characteristics looks like something like this, right? This is the Zener diode IV character. But what idealized model we will use? We will use idealized model, right? In that case, my IV characteristics will be something like this. So let me change the color. It will be like this, and it will be something like this. Right? This voltage we'll call VD, which is, is for silicon diode. It is in the silicon diode. It is in the range of 0.7, zero point 0.6 to zero point 0.7 volt. And this is the breakdown voltage, let's say VZ minus VZ, right? This is 0, this is I, this is your voltage axis. Okay, so this model we are going to use in this circuit analysis. So what is the first step? The first step you to recognize that this is a simply an inverting amplifier, right? So let me blow up the picture. we'll go to this page. Okay, so this is my circuit, right? So now first point to note that when Vi is 0, what is my V naught? When my Vi is 0, that means this is 0, then this is grounded, right? And eventually my V naught will also be grounded, right? Because this will not conduct, and it is simply this V naught will be shorting at this point, right? So my V naught will also be 0. Okay. So uh, at the origin, my if I draw the plot, this is my V naught, this is Vi. So when my Vi is 0, my V naught is 0. That means the transfer characteristics or V out versus V input will pass through the origin, right? Now let us see what will happen when I increase Vi. Vi is greater than 0 and I increase it, right? What will happen? This diode, see earlier my V naught was 0, right? For this diode to start conducting, it requires certain amount of voltage, right? This until unless my V across the diode, this is voltage across the diode, this is this much or zero point 0.7 volt, till then my this circuit, this will be turned off, right? Then just above 0 or 0 plus for certain amount of voltage, input voltage, I will be having only this path, right? And what is this path? Then my circuit will be simply this. This circuit is very familiar with you, right? This is my RL, this is 2R, this is R, this is Vi, this is V naught. So what will be my V naught by Vi? V naught by Vi will be simply 2 minus 2R by R, right? This is minus 2. So for a certain amount of time, this is my characteristics, right? When my Vi is just positive, so just some positive voltage above 0. What will happen after that? As soon as my you see your this potential is started to rise, right? This potential is started to rise, has started to rise. So the voltage across your diode will start to rise, right? Because, or you can say in this manner that let us make this point grounded, and as my input voltage starts increasing, my V naught will start decreasing because it is a negative gain, right? For 1 volt for the in this region, for 1 volt of Vi, I will have minus 2 volt of this my V naught, right? So the voltage across diode is increasing, means the diode is getting into forward bias, right? So as soon as it gets zero point 0.7 volt, as soon as it gets zero point 0.7 volt across it, so my this diode will be short. And why this diode will be short? Because beyond 0.7 volt across the diode, I have infinite amount of current, right? Infinite amount of current means I have simply a short, right? So I will have this configuration. So let's say Vi greater than certain value, let's call it Vx. My voltage across diode is more than 0.7 volt, so diode will be short. As my diode will be short, or let's say it is replaced by a voltage source, what will happen? There will be a certain drop, but current, infinite amount of current will flow, right? Let's say with a voltage source of 0.7 volt. So how will be with the configuration? Then my circuit configuration will be simply this, right? This is my RL, this is V0, and then I will have a simply a voltage source of certain voltage. Let's say it is 0.7 volt, right? And what about this path? This path, this will not conduct at that time, right? Why? Because all the current which is coming here will flow in this path, right? In this path. So you see, now what do you have? What configuration you are having? Let's say you have a virtual short here through this negative feedback path, right? So what is your V out then? Your V out will be minus 0.7 volt, irrespective of anything what is happening there, because there is a voltage source across it. What is the definition of voltage source? Voltage source does not care how much current it is flowing through it, but it holds a constant potential difference between two nodes, right? So your V naught will be always minus 0.7 volt. So after some time, your V naught will be for a certain amount of Vi. After certain amount of Vi, your V naught will be fixed at a voltage of minus 0.7 volt, right? I think this much is clear. So now let us move into the other side. Now let's say, what if Vi less than 0 and I start it reducing, right? What will happen? This part will not be there because my diode will be in reverse biased. Why my diode will be in reverse biased? Because at this instant, at this voltage, my at 0, Vi equal to 0, my V naught is 0, right? So as I start decreasing my Vi, the other hand of the P side of the diode will have negative voltage, and N side of the diode will have 0 voltage, V out, VO, right? So that diode will be in reverse bias. So there will be no current flowing through it. Or I would say that this region I am talking about, right? No current is flowing there. So it is an open circuit. So what will be my configuration? My equivalent circuit will look like nothing but this one. Whatever I have drawn in black, right? So this will be my circuit during that time. And simply I know that in this case my V naught by Vi is minus 2. So this line what I have drawn will keep continuing with a slope of minus 2, right? Slope of this line is minus 2. Okay. So now let's go to the final case. Now say Vi is much less than 0, right? And it is reducing. So at one time it will be such that your see your V out, in this case your V out is reducing as I am reducing, or I would say rather your Vi is increasing in the positive side, right? And your V out and Vi is, as Vi is decreasing, right? That means as I am going from this direction to this direction, my V out is increasing, but my VI is increasing in the negative side, right? So what will happen then? After some time, there will be a potential such that my this point is ground. See, you will encounter this kind of situation. Let me just add another page. You will encounter this kind of situation. You have this Zener diode, and let's say you had a resistance, right? So this point is increasing, this is fixed at 0. Let's say what will happen? The reverse bias, the potential across this diode or the reverse bias will keep increasing. Now let's move on to this plot. If I keep increasing to this side, at some point whenever the voltage across this is set to Vz, right, minus Vz, then I will have breakdown, diode Zener breakdown. And when I will have Zener breakdown, then I have infinite amount of current. That means I am having a potential drop, but I am having a, so this path will not flow, there will be no current through this path, and act as a it will act as a voltage source of reverse polarity, right? This is my Vz. The same circuit we have discussed in the voltage regulator case, if you can remember, right? So what will happen at that case? Then my, if this is 0, then my V naught is getting pinned to this Vz voltage, right? V naught will be nothing but Vz, because this end is ground. So your V naught will be pinned at Vz, right? So this is how your characteristics will look like. So this is your I would say this is your region 2, this is region 3, this is your 2R. Okay, I made up some mistake in the colors. I think yes, this is your region 1, this is 2, this is 3, and this is the case 4. What is here? This is your 1, this is 2, this is your 3, and this is your 4. And also it should pass through the origin, right? Because when Vi is 0, your V out will also be 0. Okay. So this will be how the characteristic, will look like. So if you can see that your option B is correct, right? So this is a pretty simple circuit. Just you need to understand how the Zener diode works, right? So your B is the right option. So let's move on to next problem. Okay. So what are they asking? They're asking that what is the form of transfer function of of the circuit shown in the figure. So what is transfer function first of all? Suppose you have a system, right? This is your output, this is your input, okay? And this is say your this system, right? So generally we define it in the frequency domain. And by the way, what is your this YT? YT is nothing but your convolution of this, right? XT into HT. This you must have studied in your signal system course, right? So if I look it in frequency domain, what will happen? Let me take Laplace transform in both sides. So what is my convolution in frequency domain or Laplace domain? It is a multiplication, right? So your ys will be hs into x of s, right? So your h of s is y of s over x of s. This is what we call transfer function, right? Now in Fourier domain, in Fourier domain, we simply replace x s equal to generally j plus sigma plus j omega. Sigma is accounting for your losses, and we take generally sigma equal to 0. So your h of j omega becomes y of j omega over x of j omega. The main point to focus here is that x is your input and y is your output. It can be anything. It may not be, it is not necessary to for this to be voltages. It can be currents and any quantity basically. And again in this context, so how will you calculate your power spectral density? Your, let's say, power spectral density of y is sy of omega is nothing but h of j omega whole square into your power spectral density of input, right? Sx of omega, or say j omega. Okay, this is output PSD, power spectral density. This is input PSD. Okay, so you should remember these things. So if we have to solve this problem, how will you go about it? This is pretty simple actually, because you see your C is in Laplace domain is nothing but 1 over SC, right? And resistance remains same. This input I will take at Vi of S, and output I will take Vo of S, right? So what is my this Vx of S? Let's say it is Vx. So I can write simply that Vx of S is R1 over R1 plus 1 over SC, right? Simple voltage division, right? We will treat the elements as impedances, right? And we will use impedance division or voltage division formula, right? Simply this is Vi of S, okay? So your, and what about this loop? If I see this loop, this is Vi of S minus V, and due to virtual short, this will be Vx of X divided by R2 is the current flowing in this loop, this branch, and that is Vx of S minus V out of S divided by R2. This is R2, this is R2, right? So this gets cancelled. So what do I have? I have Vi of S minus 2 Vx of S is equal to minus V out of S, right? So what is Vx of S? This is Vs minus 2. If you just simplify it, SCR1, and it will be 1 plus SCR1, right? Minus V out of X, and this is Vi of S. So your V out of S by V in of S will be nothing but 1 minus SC minus of 1 minus SCR1 over 1 plus SCR1, right? So this is your H of, let's say, j omega would be your minus 1 minus S will be j omega CR1, and this will be 1 plus j omega CR1. How can you write this? You can write this as 1 minus j omega by omega 0 This is 1 plus j omega by omega 0, right? What is omega 0? Omega 0 is 1 over CR1, right? Did you see it? So if you notice the steps carefully, so you will find the nature of this transfer function to be of the form. Let's say this is some constant. It is constant is here -1. It can be anything after normalization. So the form is in this, right? So this is how the form of the transfer function look like, right? So what is the form of the transfer function then? The form of the transfer function is similar to answer B, right? So this is how you calculate transfer function of any given system. So let's move on to next problem. What they're asking for the op-amp filter shown in the figure. The filter type and the 3 dB frequency are respectively this. Okay. So they want us to find out what is the filter type. So first of all, there are many ways to solve this problem, right? First, I will go with the same method I used in problem number 2. And what is that? You simply play it like this. This is your ground, and everything I will do it now in Laplace domain, right? So this is your Vi. By default, I am when I am writing here Vi means Vi of S, right? So Vi over this R1, say your R1 is for simplicity, let's see, this is R1 Vi over 1. This current has to flow through this entire contraption, capacitance and resistance, right? So this will be 0 minus V out over R2 parallel 1 over SC, right? So your Vi over V naught is equal to minus 1 over R2 by SC divided by R2 plus 1 over SC, right? Which is nothing but R2 by 1 plus R2 SC. That is nothing but 1 plus R2 SC over R2, right? So what is your V naught by Vi? Your V naught by Vi is nothing but R2 over 1 plus R2 SC with a minus sign, right? This much you have found out. Now you are asked to find out what is the type of the filter. How do you do that? You simply, you can write it in this, right? This is the filter transfer function. H of j omega is nothing but minus R2 by 1 plus, this is your j omega c R2, right? So your what is mod of j omega? Mod of j omega is R2 over root over 1 plus omega square c square R2 square. One thing you can just put it and plot it in MATLAB, and another way to do it in analytical problems. How will you do it? You first put omega equal to 0. See, if omega equal to 0, your mod of hj omega or transfer function is nothing but R2, right? And what if omega is infinity, means very high frequency? Then this becomes nothing but 0, right? So you see, The transfer function of the filter is such that it passes low frequency and stops high frequency. What is that kind of filter? That kind of filter is called low pass filter, right? So if you plot the characteristics of mod h of j omega versus omega, you will find out this something like this kind of nature, right? So this is the nature of a low pass filter. Why it is low pass? Why it is called low pass? Because it passes the lower frequencies, right? So again, next thing is how to calculate 3 dB frequency. What is 3 dB frequency? 3 dB frequency means your gain should be, or gain, or rather say transfer function. Your transfer function should be transfer function at 0 frequency divided by root 2, right? And why it is so? Now let me convert it into dB. 20 log mod h is equal to 20 log mod h of 0 minus 20 log of root 2, right? If you calculate this, it will come out to be 20 log of h of 0 minus 3, right? So this is how it is called 3 dB frequency. So your 3 dB frequency will be where your this was R, right? When it is 0, omega is 0, so your this entire denominator will be 1, so mod of h omega will be R2, right? This is R2. So the frequency, this is omega 3 dB, and at this point my amplitude will be R2 by root 2, right? So if you see from this expression, let me copy this expression. This is also, by the way, called half power point, right? Half power bandwidth. Why it is called bandwidth? Because we are talking about this much band. This is also called sometimes half power bandwidth or 3 dB bandwidth, right? You see why the nomenclature is like that? So now if this is to be equal to R2 by root 2, right? Then this quantity should be 1. Can you see that? Because this is plus 1 and by root 2 means this quantity has to be 1. That means your omega should be nothing but 1 over RC, right? Omega 3 dB is nothing but 1 over RC. So what is your F3 dB? 1 over 2 pi RC, that, sorry, R2C, that is your 2 into pi into, what was your R? Your R2 was 8.2 K, right? 8.2 into 10 raised to 3, and what was your C? 50 nanofarad. So 50 into 10 raised to minus 9. So if you solve it, it will come out to be around 388 hertz, right? So you see your B is your right option, right? So this is one way. Let me write it method 1. Method 1, okay? So this is how you can find what is the type of the filter and what is the 3 dB frequency. Another way, an intuitive way, how do you find out that what kind of filter is this? Just let me copy this circuit. This is method 2, right? See, what you can do, you need to check the input signal frequency, right? Understand this point very carefully. What I did to find out how it is a whether it is a low pass filter or not, I checked whether at omega equal to 0, how is my response, and omega equal to infinity, how is my response, right? So when my omega equal to 0, that means S equal to j omega equal to 0. That means my Vi of 0. What is Vi of 0? What kind of signal is this? It is nothing but your DC signal, right? Because DC signal has 0 frequency. If it is my DC signal, suppose you provide a DC signal at the input. So this DC signal will translate to this point, right? And if this DC signal translates to this point, then what is the and this signal? Suppose here is a DC signal. So this capacitor will not allow to pass any DC, right? So simply my circuit will become this, right? Simply my circuit will become this, and what is the output in this case? Output is nothing but minus 8.2 of Vi, right? So we have some finite output, finite non-zero output, right? So I can see that at zero frequency, or if I apply a DC signal at the input, the system or the open filter allows me to pass the entire some of the DC component to the output, right? So it does not block the DC. Basically, the point is that now you say you apply a very high frequency signal. Let's omega tends to infinity. That means I am applying a AC signal, right? And my capacitor is shorted at that time. So how will my circuit look like at that time? My circuit will look like simply this, right? So what can you see? What is my VO at this point? It is 0, right? How it is 0? Because this is in negative feedback, this is virtual short, so this is 0, and this point is directly connected to output, right? So my output will be 0. That means as I increase my frequency, and if I go to infinite frequency of the input signal, then my output becomes 0, or it blocks the complete signal. There is nothing coming out at the output, right? So it blocks high frequency signals. That means this kind of filters, we can conclude that this kind of filter is a low pass filter, right? Okay. So this is how intuitively you can tell whether it is a low pass filter or it is a high pass filter. Again, how to calculate this? So we got this expression, right, from Laplace transform. So what is the solution of this? S equal to 1 over R to C, and that is nothing but your pole location, right? You guys should be aware of poles and zeros if you have gone through the Week-8 lectures of Professor Patil, right? In the transfer function, if I have two things, right? One is the denominator, one is the numerator. If I solve the denominator, then the roots of the denominator are called poles and the roots of the numerator are called zeros. Basically, if you have a transfer function like this, say s plus z1 plus 1, s by z2 plus 1 plus s over zm plus 1. Let's say some gain is there, DC gain, and also let's say s by p1 plus 1, s by p2 plus 1, right? And in such a way s over pn plus 1. So the what are the pole locations? Pole locations are s poles are s equal to p1, p2, pn, right? And what are the zeros? Zeros are s equal to z1, z2, zm, right? And why it is called poles and zeros? Because at the pole location your magnitude of the transfer function blows up, right? So basically you see, whenever you encounter your first pole at s equal to p1 and say p2 is greater than p1 and so on. So at this point you will encounter your minus 3 dB point, right? You can see at this also, this was the pole only, right? This is the pole only at which you have this 3 dB, right? From this solution also see, this is the pole location. Pole is at 1 by R2C, right? So this at pole location you have your 3 dB frequency. So if you are able to find out your transfer function just by looking at the pole location, you can tell that whether it is what is the 3 dB frequency, right? So this is pretty simple. So there are other methods also to solve this circuit, but these are the most convenient methods. One is your rigorous analysis. Another way is to just simply look at the filter, use your intuition, apply DC, apply infinite frequency, and check what is your circuit paths, right? And then you will be able to say that whether it is a low pass filter or a high pass filter, right? So let's move on to next problem. So what was the answer, by the way? Yeah, answer was B. So if I move on to next problem, they are asking what is the form of transfer function of this circuit, right? How can you say the transfer function without writing a simple line, a single lines, right? Same intuition you can use. If you apply zero frequency, right? What will happen? This capacitor will block your DC. So this point will be simply connected to V out. So your V out will be 0 at DC, right? You have a that means you have a 0 Z1 at 0, S equal to 0, right? And also another way, also you can see that there is a pole also, right? There will also be a pole. How can you say that? Now suppose you apply infinite frequency, right? This capacitor will be short and you will have certain response, that is minus R2 by R1 of Vi, right? At omega tends to infinity, you have V naught equals to minus R2 by R1 into Vi. So you have a this your non-zero output. That means you can conclude that this filter passes high frequencies and stops low frequencies, right? So it is of a high pass filter nature, right? And the transfer function will be of the form, you have a zero, this zero at, or let me just go in the Laplace domain and then come back to this. You have a transfer function of the nature some k, you have s over s by p1 plus 1, and if you do it in Fourier domain, then you will have this k j omega over some j omega by omega naught plus 1, right? Some omega naught or omega 1. So your answer is D, right? This is how from intuition you can tell. Basically, what you are doing at 0, you see you have 0 output, right? But after some time, you have some constant output, right? This is your mod of h j omega, and this is your omega, right? So at this location where you have 3 dB less power, or it's 1 by 2 of, let's say this is V, let's say this is A, so this will be A by root 2, so this will be your omega 3 dB, right? This is a way you can, just by looking at the circuit, you can tell how the transfer function will look like. But I will do the rigorous analysis also to see whether I was right. So to do the rigorous analysis, let me just simply make the circuit. This is V naught, this is RL, this is R2, C, this is R1, this is VI, right? So what is your Vx is 0, so your Vi over R1 plus 1 by SC is nothing but minus V naught by R2, right? I am applying KCL at this node. This I am equating to this current. So what am I having? This into SC over 1 plus SC R1 is minus V naught by R2, right? So your V naught by Vi is nothing but minus SCR2 divided by 1 plus SCR1, right? So this is your H of S is equal to minus, let me take CR2 outside, so it will be S over 1 plus S by 1 over CR1. Okay, so if I just do it in Fourier domain. So it will be this. This is j omega. This is 1 plus j omega by omega 1. So your omega 1 would be 1 over CR1. So, and this you can replace it as with k, right? So your form of j of h of j omega would be k j omega over 1 plus j omega by omega 1. See, the same result you are getting, right? Oh, let's say, let's make it omega 0 for the sake of continuity. Okay. So this is how you can simply solve the transfer function of this kind of circuits. Okay. Let's move on to next problem. Okay. Again, they want us to figure out how the transfer function would look like. So this I will do more rigorously. You can simply put the logic. I will again explain how to put the logic, right? So simply what you need to do, let's say this is Vx. So your Vx should be, by the way, this Vx is nothing but Vx of S. Same in the last problem also. Okay. Please follow the notations carefully. So your Vx is nothing but R over R plus 1 by SC into Vi, right? So this is nothing but SCR over 1 plus SCR into Vi. So what is this? So this would be nothing but 0. If I apply KCL at this node, this is virtual short. So 0 minus Vx by R1 is equal to Vx minus V0 by R2, right? So your V0 by R2 will be nothing but Vx over 1 by R2 plus 1 by R1. So your V0 will be Vx into 1 plus R2 over R1. And what is your Vx? Your Vx is nothing but R over 1 R, sorry, your Vx is nothing but SCR over 1 plus SCR into Vi into this term, right? So if you do H of S equal to V naught of S by Vi of S, it is nothing but your CR 1 plus R2 by R1 over S over 1 plus SCR. So if you do H of J omega, it is in the form K J omega over 1 plus J omega by omega 0, right? Here your K is nothing but CR 1 plus R2 by R1, and your omega naught is nothing but 1 over RC. Okay, so your this form is correct. So this is pretty simple, but how do you do it intuitively? Intuitively is the same thing. Suppose you apply a 0 f equal to 0, or f equal to 0 is same as s equal to 0, because s equal to j omega, omega is 2 pi f, so f equal to 0 means s equal to 0, right? So suppose your f equal to 0, that means this will not be there. Capacitor blocks your DC. So this is simply connected to ground with a resistance. So this is a ground, right? This is a ground. This will also be a ground. That means your at f equal to 0, V out is 0. At f tends to infinity or very high, what will happen? At that case, your this is kind of short. So you are applying your Vi here directly. and it is just nothing but non-inverting amplifier, right? So your V out will be 1 plus R2 over R1 into some V of I, right? So it is the nature of this is a as a high pass. So it is a HPF, right? This is the analytical way how you can analyze this circuit. Okay, just let me shift this. Okay, and also F equal to 0, open. Okay, okay. So this is how you analyze this kind of circuits. Okay, so let's move on to the next problem. Okay, this is quite interesting. Okay, let me choose red color. An op-amp circuit is shown in the figure along with the input voltage waveform. Which graph correctly describes the output waveform, right? So this is your input waveform and this is your circuit, right? So again, first what do we check? We check whether the transfer characteristics or V naught by Vi will pass through 0 or not, right? That means whether the system is 0 input, 0 output system. That means when Vi is equal to 0, what is my V naught, right? So if Vi is equal to 0, I see that output will also be 0, right? So your V out is also 0 volt. So one thing rest assured that when my V input is 0, my V output will be 0, right? Now let me apply a positive voltage when I am at the positive cycle, right? When I am at this cycle. When I am just putting some positive excursion, what is happening to the VD? VD is nothing but V plus minus V minus. VD is trying to increase, and VD as it is trying to increase, this is trying to be positive. Some very minuscule also, but it will be some positive value. So my this diode will be on, right? Because earlier my V naught was 0. So during the positive half cycle, when Vi is greater than 0, then let's say this is Vx. My Vx tries to increase, which makes my diode D on, which makes this in this total and let me draw the circuit at that case. This is Vi and this is the feedback path, right? This is on diode, this is minus, this is plus. So what is my V out? My V out will simply follow my V in because my negative feedback is in place and my everything is ideal, right? So at the positive half, my output will simply follow the input, or I would say that the gain is 1, right? Now what about when Vi tends to 0 less than 0? If Vi less than 0, my Vx tends to be go down, right? Because see, this is my output so far. At this point, my what is my V out? My V out is 0. How? Because my V in is 0 at this point. From this condition, at this point, my V out is 0. So the N terminal of the diode is connected to 0. Now if I try to go into the try to apply negative voltage at positive terminal of non-inverting terminal of the op-amp output or Vx will try to go down, right? If Vx tries to go down, then simply my diode will be off, right? If my diode is off, then what is the circuit configuration? This is my Vi, this is my Vo, right? And there is no path in between. This is a open circuit. So there is no feedback in place, right? If there is no feedback in place, what will be the value of V0? V0 will hold the value which it got last set. It last was set at this voltage, right? 0 volt. So my V0 will remain at 0 volt, right? For the entire negative cycle. As soon as again I am in the positive cycle of the input, then it will switch back to this, right? So what is happening basically? Let's say this is case 1, this is case 2, this is case 3. Okay. So if I just simply copy the input waveform, if I simply copy the input waveform, right? Now what is happening? At this point, my circuit is in case 3, right? Then what color did I then as soon as it is in positive half cycle, it is in case 2, right? Again it comes back to case 3 at this point, right? So then when this condition is starting to play, then what will happen? The output will hold this value. And what is this value? What was that value? What was set at the case 3, and that is V naught is equal to 0, right? So your output will then be like this. And then again your positive cycle, and then again it will be in case 3, and this is nothing but case. Okay, sorry, this is case 1. This is case 1, yeah. This is case 1. Then it will go to case 2, again case 1, again case 3, again case 1, then again case 2, right? So how it will your output look like? If I draw the output waveform, your output waveform will simply look like this. It will simply act as a half wave rectifier, right? This is 1 volt because the gain we found out to be 1, and at this place it will just simply remove the negative half cycle. So this is your V out, this is your T, and again it will go to this. Okay, so this is how you analyze this kind of circuits. This is your output waveform. Okay, let's move on to next problem. Okay, similar kind of circuits, but there are two paths, right? So how to analyze this kind of circuits? Again, you see, first thing first, at Vi equal to 0, at Vi equal to 0, my this is 0, right? This will be off. This will simply be transferred to this. So my V out will be 0. Okay. Now, when I am in the positive half, right? Suppose I am increasing this voltage. If I am increasing this voltage, what will happen? Now let's say Vi greater than 0 and increasing, right? What will happen? This voltage will try to increase, right? If this voltage tries to increase, then this diode will be forward biased. So my circuit diagram will look like this. This is your Vi, this is your R1. Let's say this is 1K, this is 1K, right? So there is a negative feedback across the diode. So this will be grounded. Let me use another color. So this will be grounded. This will be grounded. And earlier this was 0, right? Last value. So this diode does not conduct. You get it? This is grounded, these two nodes. So, and I have negative feedback across this op-amp. So my V0 will keep the same state what it was holding, and that was this case, right? So my V0 will be simply 0, right? Did you get the point? If you followed the last problem very carefully, then I think this is pretty easy, right? As I am increasing here, it is increasing, tries to increase here. If this potential is trying to increase, diode, this D1 will be on, D1 will be on, and if I am assuming it to be ideal diode, so it is simply, there is no drop across it, because ideal diode characteristics is just this, right? If this is my I axis, this is my V axis, this is my ideal diode characteristic. So my V0 will hold the same value which it was earlier set when I was at this point. At this point, my V0 was 0, right? So now let's move on to this case. When my Vi is less than 0, that means when this is trying to drop, this will try to drop, and this voltage was earlier set at 0. So this diode will does not conduct, right? So D1 is off, or D1 does not conduct. So what will be my circuit diagram now? And this path does not. Okay, just let me do that. Okay, let us leave it there. So I have this resistance path, right? this is what I have. Now if your Vi goes down, this goes down, this tries to go down, right? What happens to this? This will again try to go down. If this tries to go down, then my this will be in this will be in what? This will be in forward biased. So I can simply connect my circuit like this, and this was open, right? And this was 1K, this was 1K. What is this kind of contraption? It is nothing but your inverting amplifier, right? So your V0 will be nothing but minus of Vi, right? And what does that signify? If your Vi is like this, your Vout will be like this, right? So what did we find? If I am to draw the output graph here, how will it look like? Let's say this is VO, this is T, and let me draw some lines. So your output will look like nothing but it does not allow to take your positive cycle to flow, right? And your negative cycle is inverted. That means your negative cycle, this one, this triangle will be simply inverted. Again, the positive cycle it will hold and your negative cycle will be inverted, right? So this is how the plot will look like, the output. So this A is not correct, B is also not correct, B is just the opposite. Yeah, C is your right option, right? So this is how you analyze this kind of circuits. Okay, let's move on to next problem. You just think it about for 1 minute. So one thing to notice here that this contraption is nothing but a voltage buffer, right? This we have discussed in the last lecture. That means if you have a contraption like this, this is your, let's say, Vx, this is your V out. So what is your V out? The circuit is in negative feedback, right? The op-amp is ideal. Then what about your V out? This will be virtual short and your this voltage is directly connected to V out. So V out is nothing but Vx. This can be represented as a gain block of 1, right? It is nothing but a voltage buffer. And why voltage buffers are required and all, this I have discussed in last to last session, right? Why we require voltage buffer in circuits and what role does it play. So now I need to simply analyze this part of the circuit, right? So let's analyze this part of the circuit. So if I know my Vx, I know that my V out will simply be Vx, right? That we have seen from from the last page analysis. So now what happens? The what is the input waveform? Input waveform is same, that same triangular waveform, right? Symmetry, 50% symmetry, triangular waveform. So suppose you apply positive voltage here, right? If you apply positive voltage here, then here you have positive voltage, right? Here you have increase, here you have increment. So what is this? It will decrease, right? Because in an op-amp, in the inverting terminal, if you have a positive tendency, the voltage is pushing up, then the difference of the Vd, this Vd is going down. That means your output is amplified and going down. That means your diode will be off, right? When your Vi greater than 0, your diode is off. Then that means there is no feedback, right? That means this path does not exist. So what is the voltage at this point? Vx. This voltage is translated to here, right? So your Vx will be nothing but your Vi. Do you see this? Because if there is no current flowing inside, because your op amp is ideal, this is also not there present. So all the current will flow from this direction, right? And if this is a open, or this is open, because next stage also it is going here, also no current is there, because you see it is going into the this positive terminal of another ideal op amp. So simply it is an open circuit. That means this voltage will translate it to that Vx. So your Vx is nothing but Vi in the positive cycle, right? Now what about negative cycle? What about negative cycle? Let me draw the circuit diagram. This, right? This is your circuit. This is R, this is R, this is your Vi, right? So if there is a tendency to go down, there is a tendency here to go down, that means this will go up. That means your diode is on. And if your diode is on, I can simply make this circuit as this. And this, you see, this will be a very familiar form to you, right? This here was your diode was shorted. And this is your Vx. This is your Vi. So what is your Vx here? You see, this is nothing but an inverting amplifier of gain -1, right? So your Vx will be nothing but minus of Vi, right? So you see, at positive half, your Vx is Vi. That means your V naught is Vi. At negative half, your Vx is minus Vi. That means your V naught is minus Vi, right? So how will your output look like? Let's say blue was your input. Let's say this was your input. So how will your output look like? Your output will be positive cycle, it will just simply follow, and negative cycle, it will simply invert, right? So it acts like a full wave rectifier. This is your T axis. Okay. So your output will be D. Your answer would be D, and your output will look like a full wave rectified waveform, right? So these were pretty simple op-amp circuits, right? So now let's move to the next problem. Okay. Henceforth, we'll discuss about some Bode plot issues, right? So Bode plot, I have briefly discussed above. I have briefly discussed above this, how your transfer, what is your transfer function and how it is look like, right? How it looks like. So Bode plot, what is the difference between this plot and Bode plot? The axis is different, right? The y-axis here I have taken at linear scale. In Bode plot, we have to take as dB scale, that is 20 log base 10 of this quantity, right? So if I have to draw the Bode plot of this plot, so this is your 20 log base 10 h of s mod h of s, right? And this is my omega. So what do I see? I see that there is a zero. There is a zero at this. Okay, let me just not mention what is this point on the dB scale. This is not zero, okay? So your output will, this is not zero. Let me mention it explicitly. So you have a zero. You have a zero at s equal to zero. Let's write down the zeros. Your z1 is at zero. And what are the poles? Your poles are at P1 is at 100, P2 is at 1000. Your zero contributes to plus 20 dB per decade slope, and this will contribute to minus 20 dB per decade slope, right? But these things will change if your poles are coming into right hand side or the left hand side of the axis, right? You see, so far we are discussing this is your j omega, this is your sigma, this is your s plane, right? So we are discussing about left hand side poles only as of now, okay? But if the poles are at right hand side, this conditions will not be valid, okay? So as of now we are discussing about for left hand side poles. So left hand side poles will contribute to minus 20 dB per decade slope, right? So your Bode plot will look like something like this under Bode approximation, right? What does Bode approximation say? That you take the corner point of the pole. Pole is the corner point, but ideally, what is that? Ideally, your Bode plot will look like something like this, right? This is the asymptotes. What is said under Bode approximation? Basically, at this pole location, you have a 3 dB difference. This we have already discussed today, right? But under Bode approximation, we will take the blue curve. Bode approximation, right? So this is your 1 0 will be at S equal to there, there is your Z1. This is your P1 equal to 100 and your P2 equal to 1000, right? And what about the magnitude plot? How does the magnitude plot play under Bode approximation? A 0 contributes to plus 90 degree and poles contributes to minus 90 degree, right? So at the beginning you start with 90 degree, right? Then you fall at this point. Okay, why did I mention this P2? P2 is not here. P2 will be at this place, right? So this slope is minus plus 20 dB per decade. This slope is 0 dB per decade, and this slope is minus 20 dB per decade. Okay, so this is your P1, this is your P2. So at P1, after at this your this will be like this. So from this to this, you see you have a drop of 90 degree, right? And again at P1 it will be around your 45 degree, and P2 it will be minus 45 degree, and it will drop asymptotically to minus 90 degree, right? This is your 100 and your S is 0, right? Your 0 is at 0 and P2 is 1000, right? So what are they asking? They are asking at a, this is omega axis, remember it. This is omega is 2 pi of f. It is not f, it is 2 pi of f. So at a frequency of 2 hertz, at a frequency of 2 hertz means where do we lie? We lie very near to 0, right? What is the slope obtained by Bode approximation? The slope here is 90 degree, right? So C is your right option. And how to do it in the mathematical sense? In mathematical sense, if you just have this transfer function 20 of, this is 20 of S and S plus 100, S plus 1000. So at F equal to 2 hertz, that means omega equal to how much? It is 4 pi, right? 4 pi. This is much less than 100 and 1000. So what will we approximate this under Bode approximation? Bode approximation, your HS will be 20S divided by 100 into 1000, right? Because I can simply ignore the S because S is very small in these two cases. So now if you take the angle of H of S, it will simply be 90 degree, right? This S corresponds to 90 degree. And how does this S corresponds to 90 degree? Simply you write HS is equal to some constant. Let's say this is 2, this is 3, 10 to the power 5, and say this is your value, right? So what is your H of j omega? H of j omega would be your 20 by 10 to the power 5 into j omega. So what is your angle? nothing but tan inverse of something, this 20 omega by 10 to the power 5 divided by 0, right? So tan inverse infinity, and what is that? That is pi by 2 or 90 degree, right? This is how your Bode approximation come into picture. This is the pictorial representation, and this is your mathematical norm. Okay, in both way you can do, but you should be able to visualize the Bode plot, and under Bode approximation, just by looking at the transfer function, you should be able to draw the magnitude plot and the phase plot, right? By the way, this is called your magnitude plot, and this is called your phase plot. Okay, then this axis is angle of h of s. Okay, so this is how you go about these problems. So what is the next problem? Next problem, what is the phase of this same transfer function at a frequency of 4 kilohertz, right? First thing, f is 4 kilohertz. So what is your omega? Your omega is 2 pi into 4 kilohertz, right? That is nothing but 8000 pi hertz, right? So 8000 pi means it lies in much here, right? Much beyond P2. So what is your phase there? Your phase is, you can see from the plot, it is nothing but minus 90 degree, right? So your phase from phase plot at frequency equal to 4 kilohertz is equal to minus 90 degree, right? So this is your right option. Similarly, how can you find it from this? This is your HS, this is your 20S, this is your S plus 100 and S plus 1000, right? Simply you can see here S is 8000 pi, right? S means your j omega, right? Omega is 8000 pi. So 8000 pi is much more than 100 also. So your 8000 pi is much more than 1000 or 100, right? So I will simply keep 20s above here, s from this I will keep s, and from this I will keep s, right? S gets cancel, so I have 20 by s, right? Again, your mod of hs is equal to 20 by s, sorry, not mod of hs, your h of s is 20 by s, so your h of j omega is 20 by j omega, right? And that is nothing but minus j of 20 by omega, and the angle corresponding to this is minus 90 degree, right? This way also you can do it. This is method 1, this is method 2. Okay, so moving on to next problem. What are they asking? Same transfer function. What is the slope of the magnitude Bode plot at a frequency of 500 hertz, right? So f is equal to 500 hertz. So your your omega is 1000 pi radian per second, right? That is your 3140, around 3140 radian per second, right? And what is the slope beyond your 1000? Again, if you recall this Bode plot, this plot, beyond 1000 it is minus 20 dB per decade, right? So your slope of refer plots drawn at problem number 9. Slope of magnitude plot is equal to minus 20 dB per decade. So if you would have committed the mistake that your F is only omega, then what was your 500? At 500, you would have this 0 dB per decade, right? You would have gotten the wrong answer. So you need to first convert it to omega, then check the range because the x-axis in the Bode magnitude and phase plot is omega. So minus 20 dB per decade is the right answer. So B is your right answer. Okay. So let's move on to next problem. Again, what is the slope of the magnitude plot at a frequency of 100 Hz? Again, F equal to 100 Hz, omega equal to 200 pi Hz, that is 3.14 into 200, that is 628, right? 628 Hz. That means it is lying between P1 and P2, right? P1 less than omega less than P2. And what is that range? Your magnitude plot slope at P1 less than omega less than P2 is 0 dB per decade, right? Remember this plot? At 628, somewhere here, you will have a 0 dB per decade slope or some constant gain, in other way to say, because it does not change with frequency, right? So your A would be your right answer. By the way, can anyone tell me why do we study these Bode plots? Why these are very important? I have two guests today, Gauri M. Chavan and or Mahi. Anybody can unmute and tell me why do we study these Bode plots? Because this is very essential to know. You can unmute yourself and tell me. See, these Bode plots, first of all, these Bode plots are a very powerful tool to analyze the whatever is happening in frequency domain, right, with the signal processing. Another thing that is that it helps you to analyze the stabilities, right? In later courses, you will study about these phase margins and gain margins, right? These terms are very important in circuit analysis in terms of stability. This you might have also read in control systems, right? You will say that you want your UGB. What is UGB, by the way? UGB is any point where the Bode plot crosses the 0 dB line, right? This is called UGB, unity gain bandwidth, because 0 dB means your gain is unity, log of 1, right? So you would see that many circuit analysis techniques, you want this to be minus 20 dB per decade, right? The simple reason is that minus 20 dB per decade refers to only one pole, right? One pole means your circuit is first order circuit, and your first order circuit is always stable, right? If you have seen that your RC circuit responses, your simple RC circuit responses, you would see that if you if the capacitor is discharging, it asymptotically goes to that or it charges to that, right? It never goes like second order system. You will find some ringing effect also, right? Suppose you go there and it will be ringing and it will settle. So these kind of things are of second order and higher order circuit nature. And this is the first order circuit. This is how first order circuit behaves. So first order circuits are always stable. Then you would find out the phase margins of first order circuit. Then you would compensate and do your circuit and design in such a way that your circuit mimics the first order circuit. This is one way to put it like that. Also, see, your frequency domain analysis are important because suppose you are listening to some song, right? But the sound is not coming in a clear way and you want to amplify it. Some way you get the song amplified. Your amplifier will not be linear, right? It will not be linear always. That means it will create harmonics. Or suppose you want to listen a song and it is the sound is at a say 4 kilohertz frequency, right? And but the power will all be distributed in this also 8 kilohertz, then 12 kilohertz. Then that will create a problem in your listening. When you will listen, your song will get distorted, right? This is called harmonic distortion. So how much power your harmonics are capturing or draining out of the main signal power, that you can do the PSD or power spectrum density, which I discussed very briefly sometimes 2 days sometime back. So those kind of analysis are very important. So your frequency domain analysis or this Fourier transform, Laplace transform, Z transform, Bode plots, root locus things, and Nyquist plots. These are very important things, and you should be familiar with this kind of concepts, right? So let me erase this part. Okay. So let's move on to next problem. Which of the following transfer function corresponds to the magnitude Bode plot? This is very simple. We can see that there is a zero. And how do you know there is a zero? Because it is a 20 dB per decade slope, right? From the go or from the zero, it is a 20 dB per decade slope. So you know that your transfer function will have some constant and some this. A zero at s equal to zero, right? And zeros are represented in the numerator of the transfer function. So I will simply write s. And what about this? What is this point? This point, after this point, I have a 0 dB slope, right? 0 dB per decade slope. That means this point introduces a pole. That's why your plus 20 dB per decade and your decade and minus 20 dB due to the pole is converting to 0 dB per decade slope, right? This is called your pole zero compensation, right? So after the means your s equal to at s equal to 10, you have a pole. So your s by 10 plus 1 is the form of the transfer function, right? So now how do you simplify it? You just do it that this 10s by s plus 10, right? Then your answer would be this B. And here they have taken K is 1. That you can calculate from the DC gain or gain at any frequency, right? It is 20 dB at 10. That you can calculate. How will you calculate that? You just simply take 20 dB, 20 log, then the gain equal to 20, right? That means your A is 10. So this gain is 10. Then you have to calculate how you have to calculate the gain here and equate it to this, right? But just the corresponds to the magnitude plot shown in the figure. Then you can simply see that only this part B will correspond to this kind of nature, right? So I will suggest you to further find out more salient features from this plot, right? Or you will see example, draw the phase plot. Here you see the phase plot will be between, it will start from plus 90 degree and it will fall to 0 degree, right? This thing you should be very familiar with. So just don't just solve these problems, also play with it. See how, what more you can answer from this kind of problems, right? So let's move on to this problem. Which of the following transfer functions corresponds to the magnitude Bode plot of showing in figure this? Okay. So what we can see, that there is a 0 at s equal to 10. This is a 0 because you see the slope changes plus 20 dB, right? And here it is a pole because the slope changes minus 20 dB. That's how it is becoming 0 dB. So I can simply write the transfer function as s plus your, let me write it in a conventional form, s by 10 plus 1, and this is k, let's say. They are doing k, so let us take it k1, and the pole is at 10 square, right, plus 1. So this is the way you write the transfer function. So this is k1 s plus 10 over 10 s plus 100 over 100, right? So it will be 10 k1 into s plus 10 over s plus 100. So your, this I can write as k s plus 10 over s plus 100. So your right form would be s plus 10 over s plus 100 c, right? C is your right answer. These are pretty simple stuffs, right? Let's move on to next problem for 15. Okay, 15 says what is the value of k, right? What did we find? We find out your hs to be k of s plus 10 s plus 100, right? So how can you calculate that? So you see at 0 frequency you have a 5 dB of gain, right? So h of 0 is nothing but, you will put s equal to 0, so it is k by 10, right? So 20 log h of 0 is 20 log k by 10 is nothing but 5, right? 20 log k over 10. So this is 5 over this is 0.25. So 10 raised to 0.25 is equal to log, uh, again I'm writing log, it's not log because I have taken care this from there. So 10 raised to 0.25 is k over 10, right? So your k is simply 10 raised to 1.25 and it will come out to be 17.78 or 17.8, right? So this is your answer. So these are pretty simple stuff, right? Once you get the knack how to do the Bode approximation and what a pole and a zero represents in the Bode plot, these are very easy. Okay, so again, a phase plot is given. Interesting, a phase plot is given, and we need to find the figure out the transfer function where k is a positive constant, right? How will you do that? So this is okay, fine. So when I discussed this thing, right? This plot. I mentioned that at pole locations, you will have a reduction of minus 45 degree of angle, right? And the net reduction would be 90 degree, but at the pole location, you will have a drop of 45 degree, right? See, this was 0, this was 90 degree, and there is a drop of 45 degree, right? Again, this was 0, this was 45, so again there is a drop of 45 degree, right? So 45 degree reduction in phase suggests there is a pole, and the net reduction is from either side of the pole is 90 degree. Remember? So from this plot, you see this is 0, 0 is going till here, and at this location there is a drop of 45 degree, and this side also there is a drop of 45 degree. So don't make the mistake to point these as poles, right? These are not poles and zeros, because you see a pole has to encounter for 90 degree of phase shift, right? So this is total 90 degree. That means there is only one pole here. And what is the pole location? Where it will be while there is a drop of 45 degree, right? Minus 45 degree. So this is my pole location, s equal to 10, right? So how will it look like? The transfer function will look like simply there is a constant term and there is some s by 10 plus 1, right? So let us make it k1. So it will be k1 into 10 over s plus 10. It will be 10 k1 by s plus 10, or simply k1 by k by s plus 10, right? In this form. So your A is your right answer, right? So in this manner, you can solve the problems very easily once you understand it, what a pole and a zero represents and what is the exact Bode approximation. So, okay, I think that's all I have for today. So if you have any questions regarding the session, I am open to answer. I still have 3 minutes. Else I'll go one by one what I have discussed today. First, we have discussed how the Zener diode in a feedback path will affect our op-amp operation, right? This circuit we have analyzed, and how the transfer characteristics means input transfer to output. That means input output characteristics. That is your V naught versus Vi. This is what we have got. This is what we have got. How the characteristics looks like, right? These are we have discussed. We have broken this analysis into 4 parts. You see, this is 1, this is 2, this is 3, and this is 4. Next, this problem number 2, we were to find out what is the nature of the transfer function. So first we have discussed what is the transfer function. We know that in time domain it is convolution, and it is frequency domain. The system is the nature is that it is the multiplication, right? So your transfer function would be just simply the frequency, the Laplace transform of output over Laplace transform of input, right? Then you can put your s equal to you can put the loss component or sigma as 0 and make it to in Fourier like nature. So h of j omega is y of j omega over x of j omega, right? And this one point I have mentioned, that how power spectral density is related to the transfer function of input and output. So output power spectral density is nothing but the square of transfer function multiplied by the input power spectral density, right? Then we have analyzed the circuit, simple KCL KVL in the Laplace domain, and then we have converted it back to Fourier domain because our options were given in the only j omega term, right? Then we have discussed another problem, and here I have told you how to intuitively tell whether it is a uh, low pass filter or high pass filter. And what is the process? You just apply, assume that a DC is applied and see how the capacitance or the energy storing element is behaving in that case, whether it is open or a short, and you apply infinite frequency, right? And how does that behave? So you will see that one case you will have low frequencies are blocked or low frequencies are allowed, and high, for the high frequency case it is vice versa. So from that you can simply calculate how is your behavior of the filter. And for the 3 dB bandwidth you can simply take the first pole location, right, for to get the 3 dB bandwidth. And then, but this is 3 dB bandwidth for low pass and high pass filter. For band pass filters it will be somewhat tricky, right? Because you need to, if let me just go here. See, this is a band pass response, right? This response is a band pass response. So you need to find out this frequency where the 3 dB is occurring, omega L we say that, and this pole location, and the difference will be your 3 dB bandwidth, kinda, right? So then similarly we have discussed some other topics. I have discussed what are poles and what are zeros, and how a transfer function should be written. It is not your s plus z1 and by s plus p1. It should be written in the form that s by z1 plus 1 over s by p1 plus 1. This helps you to avoid making mistake for calculating the constant term, right? So this form is what you will follow. Don't follow the simple s plus this and this, because there you do not get the gain correctly, right? Then we have discussed this case, how the nature of the transfer function will be. First, I have discussed it, how intuitively we can tell it, and then also by simple circuit analysis we have discussed. This is the analysis, how we can rigorously do the analysis and find out the same solution, right? You see, here I have just written 2 lines, and if you think it, you can just get it by looking at the circuit. What is it? Then we have discussed again the similar high pass filter, but in a different way. Here the gain term is controllable by two more resistance in the, and the capacitance is connected to the non-inverting terminal, right? And then we have seen the how the waveform shaping circuits for with op-amps. We have seen half wave rectifiers. We have seen this was the half wave rectifier circuit. Then we have seen some configuration where the alternate cycle has been rectified, and we have seen the full wave rectifier circuit, right? How the full wave will come into picture, right? These rectifier circuits are very helpful, and this helps us making precision rectifiers also sometimes. Then we move on to the Bode plot. I have discussed you how from a Bode plot you can plot the with the Bode approximation, the Bode plot, and simply the salient points, right? And the things to remember is that when we are talking about this plus 20 dB, minus 20 dB, or plus 90, minus 90 in the phase, we should remember that we are discussing about the left hand side poles, or the system is stable, right? Then we did some analysis on the Fourier on the Bode plot, and we found out the phase and frequency, phase and magnitude, or phase and or the slope of the magnitude plot for some cases using two methods, one by simply using the from the plot, and one is by the rigorous mathematical analysis, right? So this is how, and then again in the last few problems, some phase plot or magnitude plot was given. We were to guess how the transfer function will look like, right? So these things, this problem number 13, you can also relate to problem number 3 or 4. That was the circuit representation, right, of the same thing. And again 14 was same, 15 was also same. So 16 we were given a phase plot, and I told you to remember that one pole or one zero corresponds to a shift or advancement of 90 degree of phase, right? But at that location from the previous point it will have a for a zero, it will have a plus 45-degree phase shift, and for a pole, it will have a minus 45-degree phase shift. But total, including both sides, it will encounter for a 90-degree phase shift, right? So if you have any question, I still can afford 5 more minutes. Okay, so let's end the session here. Thank you for participating.